The SAR ADC, Successive Approximation Register Analog to Digital Converter. This is the first stage, which involves creating the clock signal that drives the rest of the circuit. Here is the parts table. Currently, we are using 5 volts. However, as the project progresses, we will need additional voltages, specifically plus or minus 9 volts. To get these voltages, we'll chain 2 power sources in series, one at 9 volts and one at negative 9 volts, and a 0-volt reference in the middle. The clock signal is essential for synchronizing the various components of the SAR ADC, ensuring that the shift register, DAC, and flip-flops operate in sync as they work together to convert the analog input into a digital value. The SAR ADC is a type of ADC that converts an analog signal into a digital value by iteratively approximating the input voltage. It works by comparing the input voltage with a reference voltage in each cycle. Initially, the ADC makes a guess about the input voltage, and then it progressively refines that guess using a binary search approach. This process is called successive approximation. In this case, it works by comparing the analog input voltage with a reference value, adjusting the guess value based on the comparison, and repeating the process. This iterative approach continues until the ADC reaches the desired bit resolution, in this case a 7-bit output. So I've also created code that measures the frequency and period of the clock signal. Mitsuru Yamada, the creator of this, claims that the astable multivibrator yields a period of 103 microseconds, suggesting a clock frequency in the order of 10 kilohertz. So we'll confirm this through a nano. The code uses the Arduino's micros function to measure the time between 2 rising edges of the clock signal, and interrupt is attached to the pin connected to the clock signal, in this case pin 2. Each time a rising edge is detected, the interrupt service routine, detect rising edge, is triggered. The time difference between the 2 rising edges gives the period of the clock signal, and from the period we can calculate the frequency. The code then prints the period and frequency to the serial monitor. As you can see, the values are pretty close to the values that Yamada claims. Thanks for watching.